Okay, let's talk about oxidation and the oxidation mechanism. We'll also talk a little bit about other things and like the reactivity of it and some of those things. But the main gist of the oxidation mechanism is what we care about is that it's a chromium-6 agent. And so there's a couple of different chromium-6 agents that we care about and a couple of different conditions that we can put them in, either aqueous or organic. And so we're going to look at both cases and the different reagents that we could include in on there. So we have two sides. We could either do the organic route or the aqueous route, and a lot of the times they're pretty similar. So here we have this guy. You can call him CrO3. See, CrO3. All of these are chromium-6 agents. Here is sodium dichromate, Na2, Cr2O7. Sodium dichromate. We also have potassium dichromate, basically the same thing. So these three make up what we call the Jones reagents. And so the Jones reagents react in a solution with water and some acid, some sulfuric acid generally is what we use. And we mix either this with those two, or this with those two, or this with those two, and these go to make chromic acid. We'll see what that looks like later on. We also have organic options. So right here we have what's called PDC, pyridinium dichromate, PDC. And we'll often use the abbreviated name for those. And here we have pyridinium chlorochromate, PCC. And so what happens, these don't have like a cute little name like the Jones reagents, but we mix one of these with dichloromethane, DCM. That's its solvent that we'll mix it with. So these are the main five that you're really going to concern yourself with. And what you need to know is that if you're working with aqueous, you're going to put it with water and sulfuric acid. If you're working with an organic thing, you're going to mix it with DCM, dimethyl chloride, CH2Cl2. Cool. So this is just a reiteration of what I said earlier. And so what we really care about is when we mix these guys together to make the Jones reagents, or this would be Jones oxidation in specific. This is a shorthand for oxidation. When we do this, what comes out of it is we make chromic acid. So chromic acid looks like this. It's still chromium-6. And we'll see why this is useful and how we can use that in the mechanism. These, they don't have a cute little name like Jones oxidation, and they don't even really go to make chromic acid, although they do have very, very similar reactivities. So let's look at what that might look like functionally and practically. So if, for example, we have three different scenarios that we could be in. We could be working with a primary, secondary, or tertiary alcohol. And we can have these different reactions. So I'm just going to use the same thing for all three of these. But remember, I could use any of these three with water and sulfuric acid, or either of these two with DCM, and they're going to react the same way. So these three reacting with this, all do the same thing. These two reacting with this, all do the same thing. So I'm just going to choose one thing, keep it consistent throughout. Just know anything on that list will do the same thing. So let's just say here we'll do Jones with CrO3. Remember, it doesn't actually matter what's above or below the arrow. That is irrelevant. So if I reacted this with this Jones oxidation conditions, I'm going to wind up getting a full oxidation to some like acetic acid group, a carbonyl with a carboxylic acid actually, instead of just an aldehyde or ketone. In this case, if I did PCC and DCM with my primary alcohol, I'm going to end up with an aldehyde. And so the reason for this difference is actually quite important. So this we'll talk about later. but these are actually really important to keep straight, that when we're using a primary alcohol that we want to oxidize to an aldehyde, we need to make sure that we do this in organic conditions. If we do not do it in organic conditions, we will always end up with the carboxylic acid as our final product. And so we're going to look at that mechanism later and why that's the case. Let's just keep going through these. CrO3. Versus PCC. All right. These actually are easy to keep straight because in both of these cases, we're going to wind up with the same thing. Both of these cases, we're going to end up with a ketone because that's as far as you can oxidize that alcohol to the ketone because it's secondary. Now this, I'm just going to say, this one's quite simple. So you have this tertiary, you have a tertiary alcohol. What can that get oxidized to? That can't get oxidized at all. This one is going to be a true no reaction kind of situation because we can't have, there's no proton to remove here. Just like in these other examples, I can oxidize this by removing these protons, making it more connected to something that's more electronegative. Oxidize these guys. So this is truly a no reaction situation because there are no hydrogens to remove there. So let's look at a mechanism, and let's just start looking at a mechanism with a primary situation, primary alcohol, so that we can show it going to make the carboxylic acid and what that would look like when we're doing that. So remember how earlier I mentioned that anytime we're doing something with Jones oxidation, we're going to make the chromic acid. Chromic acid. You don't need to know the mechanism to get to chromic acid. You just need to know that if you mix one of these three things with water and sulfuric acid, you're going to wind up with chromic acid. You don't need to know how or why, you just need to know that it happens. And so let's just say you were given a mechanism, and we'll do the same thing that we just showed there. We'll use ethanol going to make acetic acid. And you were told to use CrO3, H2O, and H2SO4. So you need to know how to do the mechanism for this reaction. And so first off, we can just show the chromic acid because we know that that is going to be there. That is already assumed. Now, depending on who your professor is, you might get off with not having to do much in the way of really showing out this mechanism. So let's just say it's still ethanol, the mechanism on how this gets connected. So what ends up happening is this hydrogen and this OH, these guys come together to make water. So water leaves, and this chromium and this oxygen become connected. These guys become connected. Once these guys become connected, we need to start thinking about removing one of these protons, because these protons are the things that are going to get lost to go to make the acetic acid. And so what could remove those protons. Removing a proton, that's an acid-base reaction, right? And so what is basic in the solution that I already gave you? Well, it's certainly not sulfuric acid or HSO4 minus. That is the conjugate base of a really strong acid, so it's not going to be a very sufficient base. But we could use water here. So I'm actually going to take this water molecule and I'm going to grab one of those protons. Either of them is totally fine to use. And then I'm going to take the electrons and the CH bond right here and I'm going to bring those down to make a new CO double bond. And then in doing that, I'm going to give these electrons back to the chromium. We give those electrons back to the chromium. We aren't really super concerned with what happens to that chromium. What we are concerned with is what happens to our organic molecule of interest. So we do have this intermediate where we end up making the aldehyde, just like we have for the answer for if we use PCC and DCM. The difference here is that it does not stop at the aldehyde. It's able to further oxidize. But if we did not have any water in solution, that's why we're able to stop at the aldehyde. So if we did the same reaction using PCC with DCM, this would be our final stopping point. The trouble with that is that whenever we're in aqueous conditions, there's always this equilibrium that occurs where we make this thing called a hydrate, also known as a geminal diol. We can make this hydrate. Making the hydrate is the thing that's really important to this reaction, and it's why when we're in aqueous conditions, we go on to oxidize further and further. So we can look at this mechanism later on, or you could look up hydrate formation mechanism. But let's just continue on. If we make this, what's stopping us from doing this reaction all over again? Where the chromium makes a new connection to our alcohol and we oxidize once more. There is nothing keeping us from doing that. So this takes place and we wind up with basically the same thing happening all over again. Last thing we need to see is water acting as a base to come and remove this proton here. This will go to form the acetic acid and we'll lose that chromium as a byproduct that we're not super concerned with. So this is how we end up making the oxidized version. Now, if we had something that instead of having two hydrogens, it was a secondary alcohol, we would end up with the ketone. Or if we had a primary alcohol in organic conditions rather than aqueous conditions, we could end up with the aldehyde. But because we're in aqueous conditions, we make the hydrate, which allows this reaction to go on further. And even though this reaction equilibrium very much favors the aldehyde versus the hydrate, Le Chatelier's principle pushes this forward and gets us to this final place in the end where we use up some of this, so this goes to make more of it, and as this keeps getting used up and pulled along down, this equilibrium just keeps pushing the reaction further and further because the hydrate gets used up. So Le Chatelier's principle is what pushes this reaction forward. So real quick, let's just look at the mechanism to go from an aldehyde to a hydrate so you understand that aspect of it. It's quite simple. And since we're using, this can happen in both acidic or basic conditions, but let's look at the acidic hydrate formation mechanism because that's going to matter specifically for oxidation. So here's our simple aldehyde. We're in acidic conditions, so you could assume we have H3O+ readily available. Now, in the beginning of a mechanism, like the one we've shown here, it's not just something that we can just assume we have H3O+. We want to show water and sulfuric acid interacting with one another, doing that mechanism to make H3O+. But at this point, we already know that that's been made. So I'm going to grab a proton from my acid source, because water is a better acid. Water is more likely to be my acid in solution because H2SO4 is a stronger acid than water, or than H3O+. And so we're going to go to the side of the weaker acid. We've already talked about that with acid-base chemistry. So we grab that proton. This is the intermediate that we've made. We also recognize this intermediate has the ability to do resonance, where we can move those electrons up onto the oxygen. And this really emphasizes why that carbon of the carbonyl is such a great electrophile. So now this is shown to be a very awesome electrophile. What can come in and attack this electrophile? Water. So water is a nucleophile in this case, or a Lewis base attacks the Lewis acid. Nucleophile attacks the electrophile. You could have also shown it attacking here and kicking that up. Either way is totally acceptable. Now we need to do a proton transfer. We'll move that there. And now we have the hydrate, which is the same thing as we've been using here. We can notice that this is the same as that. Oh, sounds like some of my roommates are coming home, so I guess I better finish this up. But yes, let me know if you have any questions. You can always email me, or we'll talk in our Zoom recitation, or you can leave a question in the comments if you're not in my class, and we can talk about it there. Anyway, I look forward to hearing from you guys soon. It's been far too long. I hope you're doing all right with that sheltering in place situation. Later.